I'll giving you a metaphor, maybe. Imagine all of us have seen ultrasound images. In medicine, we use ultrasound images or tomography images to have more information about the patient, about the human being. If you see a tomography image, nobody will be surprised with saying we're looking at a human. No? Then I want you, next time you see tropical objects, keep in mind you are looking at the right objects with a special machine, with a special tool that is tropical geometry. Then, exactly as the same as the ultrasound and tomography, it doesn't work for every problem. But there are some problems that are exactly the tool to be used. And the problems are very good with tropical geometry are problems with involve parametrization, intersection theory, enumerative geometry, and for example, existence of real algebraic objects. If I ask if there exists a real algebraic object with some properties, and I want to construct a tropical geometry, is a very good tool to construct real objects. And there are people saying what we want in using tropical geometry is that we want a lot of combinatorics. We have a new toolkit of combinatorics that we can use in the study of these objects. And there are people saying tropical geometry, the lemma of tropical geometry is studying simple objects, we make theorem of complex objects. Maybe I will start with the tropical algebra. Finally, what we are doing is geometry in tropical algebra, using tropical algebra. This algebra is also known as a max plus or min plus. And that's because the set we are going to take is R, union minus infinity, in this case. And in this case, I have to put this a plus instead of minus. Then we need two operations, the sum. I will put quotients to make clear it's not the usual one. And then I have two elements of this set. This is called T for tropical. Then I said that the sum of these two, the tropical sum of these two, it will be the max between A and B. And I have a product. I say the product of A and B will be the usual sum, the classical sum. Then it starts to look something about, has to do something about validation that we see this morning with Mark. And when we have these two operations and this set, we can make polynomials, we can ask what does the root of a polynomial means. And for example, this will be, with this operation, this will be a semi-ring, just because we don't have like a subtraction. We don't have a inverse of this operation. And the zero or the zero element of this operation will be minus infinity, since the sum of A plus minus infinity will be always A. But there does not exist an element, and this will be minus infinity. Then we don't have this either. And since this one is the classical sum, we have all the properties of the classical sum. Okay? There's a algebra has been studied in the beginning by Simon, a Brazilian mathematician who lived in Paris, and they say they joke with him about this tropical name. This tropical name is because he was Brazilian. There's nothing else with this tropical word. And they say they start to look at this algebra because if I have a graph with arrows maybe and weights, for example, and I have 2 points, P and Q, and I want to know who is the shortest path between P and Q. Then, if this is the distance of the time or whatever you want to minimize, you have to make all the possible paths and then take the minimum. Then you have to take a lot of sums and then minimum. And then he realized that it works exactly as monomials once you make product of length with this definition and then you take the sum over this product. Okay. Questions? Okay, then we can start to make polynomials. Then what does x squared means? So this is the same as x times x. In our classical notation it will be 2x. Okay? Then any monomial 5x to the 6 in fact is 6x plus 5. Then any monomial becomes a linear function. Okay? And if I have the sum of 2 monomials, this will be the maximum between 2x and 3x. We have the maximum between a set of linear functions. For example, if I make the graph of this polynomial, I have to take this function, 2x, and the other function, 3x, and we have to take the maximum of the 2 graphs. Then the graph of this will be in this part, 1 and this part. This is the graph of this tropical polynomial. Then in general it looks like, since we are taking polynomials, the slope of these lines are always are natural numbers, and then we will see that the graphs of tropical polynomials is a piecewise linear map, and we have some corners. The corner is exactly where 2 of these linear functions became the same, and then we have to change of monomial. Okay? Then we have, this is the graph, and we need the definition of roots. In this case, the roots will be the points where this graph breaks. The points where the function is not linear. And why is this? The definition, the classical definition of a root is a point where the polynomial is 0. In classical, we say that if f x is a root, if f of x is equal to 0. But we can always also say that f x is a root, x0 is a root. If we can write this like x minus x0 times another polynomial, as you can factorize it. Then this one is in classical geometry, these are equivalent. For tropical geometry, we're going to generalize this one, and when we generalize this one, we obtain exactly the points where the graph breaks. Okay? And then we need to define the multiplicity of a root. And for example, this one will be a root of multiplicity k if this can be factorized as x minus x0 to the k, and this one do not have this. We cannot take one of these from here. Okay? Then we need the definition of multiplicity. Okay, I have root. The definition of a root is a root of f. It's a tropical polynomial. If the maximum here, the maximum is achieved by at least two monomials. Eight. At least two monomials. This is the first definition, and we have another definition that we said that minus infinity is a root of f if is the minimum the degrees it means that the last part of the graph goes downstairs and not in right horizontal. Okay? For example, in this one, we will have three roots, and two roots. The roots are minus infinity and 0. Okay? And then we need multiplicity. As we just said, a root is the intersection of two lines. The projection of the intersection of two lines. This, for example, will have slope k1, and this one slope k2, with k2 bigger than k1. Then k2 minus k1 will be the multiplicity of this root. Then in this example, we have 0 of multiplicity 2, and multiplicity 1, and minus infinity of multiplicity 2, where the multiplicity of infinity will be the slope of the graph when we tend to minus infinity. Okay? Everything I say today will be using the max function, but we can use the minimum, and maybe in the course will change. Sometimes we will take minimum, we will take maximum. Everything is depending on the problem. You can choose max or min. Then if we have roots, we have multiplicity of roots, then we have fundamental theorem of tropical algebra. It says that if f is a tropical polynomial of degree k, or degree d, well, the degree is exactly the usual one, then have the multiplicity. The roots. It means that with this operation, the reals become algebraically closed if we add this minus infinity. This gives the real structure of where we have always the roots. Okay? And this doesn't happen in general with the reals. No? With the reals, we just see that we have at most the roots. In this case, we have always the roots. Questions? You want to see more examples, or we can just. Okay, then we can make two variables polynomial of x1. And we're going to have the same. For example, we're going to x plus y plus 1, a linear polynomial in two variables. And then this name is equal to maximum between x, y, and 1. And then again, we're going to say that the zeros of the variety defined by f will be points where the maximum of this trinomial is attained by at least two of them. Okay, then what is the picture of this? We're going to have four possibilities that x equal to y, and both of them are bigger than 1. The 1 is equal to x. And both are bigger than or equal to y, and 1 equal to y equal to x, and equality. No? Okay. And then we need this set. The union of these through these four sets will be the tropical line. Then the width. This one will be the point 1, Then I have this point. And this means we have x equal to y but bigger than 1. That means the line will stop 1 starting from 1. From this one we need x equal to 1. And from this one y equal to 1. Then this is the tropical line. And if I change here the coefficients, and none of them are minus infinitum, the picture will be exactly the same but translated in the plate. Those are a generic tropical line, a line having 3 monomers. Good? In particular, if I take two generic lines, they will intersect only 1 point. And if I take two generic points, there will be exactly one line passing through it.
Excuse me, what was this last image that you take?
If you take two generic points, there will be a unique line passing through them. The question is what the generic mean? Huh?
No. Why was this 3? Why did you draw the line like this?
Because I just said that all the lines look like this, but just translated. Okay? Then we have some special cases. What does generic mean? I mean, we cannot have 2 points having between them a line of slope 1, slope 0, or slope infinity. Besides these cases, we have unity. Okay? And exactly the same for this one. If the vertex of the other line is in one of the edges of the line, they won't meet in one point. And then I will speak that now, but there's a way of saying that these 2 lines intersect anyway with multiplicity 1. You cannot say it intersects in one point, but you can give at this edge multiplicity and it will be 1. Okay? We need the concept of tropical intersection. For example, this intersection is not tropical 1. The tropical intersection is only this point. Okay? But I will speak about it later when we will talk about this intersection theory. Okay, questions? Then I'm going to make some pictures of other tropical objects, tropical curves. For the instance, we're working on plane tropical curves. And all of them are graphs, embedded graphs. For example, this is a conic. For example, this one is also a conic. Okay? Then, as they look, they are graphs. The slope of the edges will be always rational. Since finally I'm going to make the example of two binomial to look that in fact you will always have this rational slope. For example, 3 xy plus 5 x squared y. For example. What does it mean? It means that this is the maximum between 3 plus x plus y and 5 plus 3x plus y. And the curve defined by this monomial is where these 2 linear functions are equal. Then we will have 5 minus 3 plus 1 minus 2 x plus 0 y equal to 0. 2 minus 1. I have minus 1. And I don't want to kill the y, so I'm going to put something else. And I want to have here 3 minus 1 4. This is equal to 6. Okay, and then, but in fact, if you look at this, if I graph the powers of this one, it will be 1, 1. And this one will be 2, 3. Okay, and if you look at this expression, it says that the dot product between the point x, y, and the point 2 minus 1 minus 1 is constant. In fact, equal to 2. Then it said it will be a line orthogonal to the vector that join the 2 points. And then, since we're almost going to have integer numbers here, the slope of this line will be always rational. Okay? Then, in general, a tropical curve will be a union of a graph and in order to, as a exactly the same way we define the multiplicity of a root, we need also define a weight in these edges. Then it will be a weighted graph. And the weight will be exactly the same. For example, for one variable, if we have this monomial to the power of k1, and another monomial with power k2, and then the multiplicity is the distance between k1 and k2. Now we will have, for example, here, the 0.11 and the 0.23. And it will be the integer left of this arrow, where integer left means that if we look at the lattice, we have a vector in the lattice, and the integer left is the number of points that the number of integer points in this arrow minus 1. Okay? And then we have, for example, in this one, all the weights are 1. And then here we can see the degree of the curve. We have this one and this one. It means that the weights of the edges, the horizontal edges going to minus infinity, will be 2. Exactly the same here, and exactly the same here. We can create finally we can create the degree of, or more generally, the Newton polytope of the curve. Okay? Question?
Is it possible to see the singularities of your conic, for example, in these pictures?
Okay, I'm going to go in here now. For example, this, not in the moment, because just I'm going to say that these two conics are not singular, and cannot see the singularities since they are not singular. Okay? For example, if I have, I don't know, have you been seeing this week about Newton polytope or not? I have no idea. No? The definition of Newton polytope, I can.
Sí, okay.
Okay? I can repeat. Okay. Then if I have a polynomial, and it will be the tropical zone of A, G is the one to G. Okay? And where A, E, G. Real numbers. We don't want coefficients to be minus infinity because it's the same as in classical. We don't want coefficients to be 0. Okay? Then the Newton polytope will be the convex whole. The ID that the AEG division from minus infinity. Then, for example, if I take this polynomial, the Newton polytope will be the simplex with vertices in 0, 0, 1, 0, and 0, 1. And it happens that exactly in the same way we show that the tropical curve defined by a binomial is orthogonal to its tropical, to Newton polytope. If you can see here, we have a dual picture, and the dual picture is exactly the line. For example, in this yellow conic I said, you will have this Newton polytope, that was I say is of degree 2, and the picture there is not dual to this triangle, but the composition, a triangulation of this triangle. So I have this triangulation can see that you have a duality from the composition of the Newton polytope and the tropical curve. Then going back to your question a little bit, a line, the Newton polytope of a line has volume 1.5 or area 1.5, 1/2. Sorry. And in fact, what we're going to say is that a tropical curve will be non-singular if any of the triangles in the triangulation is of the minimum area, and this is one half. Then in this case, these two triangulations are primitives, and then you don't have singularities. Okay, but for example, you can have this combination. Okay. And if we make the dual picture, you will have intersection of two lines, and you can see that here you will see a singular point, because in all the other cases, if this triangle, or this one, if its area is 1.5, you can perform a change of coordinates and see that locally it looks like a line. If the triangle is of the good area, it's enough to say it looks like a line. I don't know if go further with this decomposition. Okay, then we have the composition of polytopes, graphs with weights. And how can I say, okay, then I make a graph. And with rational slopes, how can I know that it's a tropical curve or not? Okay, this one is a graph with rational slopes, but it's not a tropical curve. And the only condition we need to guarantee that this is a tropical curve is if at every point, this is called the balance condition. If it's at every point we have weights, then for every point, vertex, we have a sum between all the edges having adjacent to this point and all the W, Y, or W, E. Just V is from A to W, E. And to each of these edges, I'm going to define a vector, primitive vector. It means that the integer length is 1. Okay, then I have these vectors. And the only condition I need for a graph to be a tropical curve is that the sum of the weight times the vector E is equal to 0. Now, in fact, it's equivalent to say that you have the composition that is dual to a composition, because finally the sum of the weights and the vectors is exactly the same that make all the tour of a polygon. You have weights and vectors, and you want this sum to be 0, and you have to come back to the 0, and then this will be exactly the polygon you are doing about. Okay? Then we have two sets. We have two sets, tropical lines. first, right? And rational balance graphs. And these two sets are the same. Okay? Then you want on combinatorics, you can think about it as the curve defined by a polynomial, or you can think about them as curves with the balance condition. Okay? No. Questions? No? Done? Okay, then for saying a little bit about this intersection theory I talked about, and we already see the case of the intersection of two lines. And the union of two tropical curves is a tropical curve. And for example, in this case, we'll have this subdivision, as I just drew it before. And I can define the multiplicity of intersection of these two curves as the area of this. Okay? And for example, if I can have my conic, and I'm going to have a line. If I make the dual subdivision, it's going to be something like that. That's where the intersections are these two squares, and this is the area of each one of them is long. The conic and the line intersects in 2 points with multiplicity 1 each of them, and then we have a conic and a line intersect with multiplicity 2. And this can be extended. In general, we have a Besut theorem or a more general version of Berg theorem. So today I'm only going to speak about this one. And then we say that C1 and C2 are tropical curves of degrees C1 and C2, both here generic. Then they not with multiplicity, the intersection between C1 and C2 will be exactly C1 times 2. Then it shows how things about multiplicity works very well in tropical geometry. We can, generally we can say theorems about tropical of classical intersection and translate them very well in tropical geometry. Okay? And before I speak how we use this in classic algebraic geometry, for example, we can make with much more variables and not only taking polynomials but ideal. And we can take ideals in the space of polynomials, tropical polynomials, and we have intersection of hypersurfaces. The hypersurfaces, tropical hypersurfaces, they won't be anymore graphs, they will be polyhedral complexes. There's a definition of this balance condition that you can give to this polyhedral complex. And for example, if we have the ideal generated by a set of polynomials, it's not going to be true that the variety defined by the ideal E will be the intersection of the hypersurface defined by the polynomial. Sometimes we need more polynomials to the idea. But there's a result that there exists always a finite number of polynomials that if you intersect the hypersurfaces, you obtain the variety of this idea. For example, curves in space will be graphs. You will have graphs in any dimension. And if this in this case we don't have the quality that I wrote before. I said balanced graphs are equal to the tropical curves. In higher dimension we don't have the result. For hypersurfaces we have this result. A tropical hypersurface is a balanced polyhedral complex with rational polyhedral complex, but with higher dimension we don't have the result. It's not true that every balanced polyhedral complex is a rational number. And now I want to show you how we can find these tropical objects in algebraic geometry. And there are two classical ways to arrive at them. One is via the algebras. Now, for example, I will take the same polynomial, a line, but this time will be a complex polynomial. Then the zero for this polynomial is a tropical line, okay? And this, I will draw the real part of this curve, and I will perform two operations. The first one is to take the absolute value of the norm of the coordinate of a point. For example, the point 3 minus 1, I'm going to translate it to the point 3, 1. I'm going to take the norm of the coordinate wise. Then if I perform this operation, I will find this, the real part will be projected in this line, okay? See? And it happens that the complex part of this curve will be filling the interior of this part.
Lucía, we don't see the left side.
Okay. Better? Okay? And then I'm going to take logarithm. Now I'm only in the positive quadrant. And I'm going to take logarithm. And obviously here we have the first coordinate equal to 0, and here the second one. And it happens that it will look like this. Okay? And from here to here is log. And then we're going to have a limit. Here we're going to have log t. And I'm going to make log t to go to 0 or to infinity, depending what we want to find. And what happens when I perform this limit is that this is the algebra I forgot to say. This object is called the middle of the line. And what happens when I make the limit when t goes to 0 or to infinity or depends, this amoeba becomes thinner and thinner. And in the limit you will find the tropical line. And obviously these operations are not very natural. You cannot imagine take the absolute value, logarithm, and limit. It's not something our brain can do easily. But here's a first picture. How can we find this tropical object? By
What is T?
t is log back, is the logarithm in place. And the limit you take it if you're using math. Okay? Okay, this is the first picture. I'm going to make another picture of how can we now I'm not going to take a polynomial in C, or I'm going to take a polynomial with coefficients in the Pisto series. Okay, I'm going to say that I'm going to use the so-called trans-final Pisto series. That is series of the form where the exponents are elements are a well-ordered subset of R. I can always say who is the first one. Okay? And I'm going to take a polynomial here. I'm going to take after this one and a polynomial j where this are transfinite. And I will ask also to be convergent near here. Oh, this one is not necessary, but sometimes we get it. And for example, again, I can take this polynomial h in C, and I want to see the valuations of the set of zeros of this polynomial. Okay? Where, well, usually in tropical geometry we call valuation, but in fact it's minus valuation. Let me please call it valuation. Where valuation here about this one will be the name I start I is different from 0. Okay? And let's think about the set of zeros of this polynomial. X plus y plus 1 is with the sum of possibly infinite number of monomials, we say. And we want this one to be 0. Then if everything is 0, the coefficient of each one of the terms must be 0. Then who is going to be the first element of this new series? We have to see of the valuation of x, the valuation of y, and the valuation of 0. Okay? And then again we have four different possibilities. The valuation of x is equal to the valuation of y, and both of them are smaller than the valuation of 1 minus the valuation of 1. And the other one, valuation of x equals 0 and both of them greater than evaluation of y. Evaluation of y equal to 0, for them evaluation of x, and the equality of the three of them. And it's exactly the same set as when we found this tropical. Okay? Then here we have this, the zero of this polynomial, x. We have the curve, well, the line defined by this polynomial. See the curve defined by f. This is the complex object, and I will make valuation, minor valuation as you want. And what we found here will be a tropical line. Okay? Then I need a definition of a polynomial f. F will be this polynomial. And we're going to define the tropicalization of a polynomial f, whose coefficients are transfinite with so series. And then we'll say that this polynomial, I'm going to make it in two variables, but we can make it in any number of variables, will be the tropical polynomial defined by the sum of AG of PAG in valuation of A and G, such that the A and G is from 0 to the I of G. Given a polynomial with coefficients with this series, I can have a new polynomial, a tropical one, which coefficients are the valuation or non-evaluation of the coefficient of the other one. And then we have maybe the so-called fundamental theorem of tropical geometry. It says take any polynomial f of this type, and you have the hypersurface defined by it. Okay? I perform valuation that is given each one and valuation is minus valuation of each one minus valuation of each n. Valuation, this one is exactly the same of the hypersurface defined by the tropicalization of f. Then if take valuation or take the norm and the limit and whatever I said before is not very natural, we have this powerful there. So it was by was said by Medrano in this setting and then extended by Fuensanta to other value fields. She generalized this Medrano theorem to some other value fields. And then here we can study this object without thinking at all of this is evaluation, this is the limit of where we have these combinatorial objects, and we know there's the image of the case. Okay? For a hypersurface or in general of an algebraic variety. Then here we can perform all the combinatorial tools we have. And even if this looks unnatural, imagine for any coordinate where you're only looking at the first exponent of this coefficient is not 0. It's the only thing you're thinking of. You forget everything else. And the power of the tropical geometry is this. Here we can recover a lot of information of h of f only looking at H of tropicals. Then we have these objects, graphs or polyhedral complexes. Then if you know how to translate a concept from H of F to H of tropical F, you can study it here and then try to go back. Then it is more or less how we work. We are thinking in tropical geometry in some concepts. We need to say which is the good definition in tropical geometry, understand what properties we can recover, and then what of these properties can be pulled back again to the algebraic variety. Then, as I said before, things, for example, as if we're looking at something, a definition or a problem involves parametrizations, involves enumerative problems, or real problems, or intersection theory problems. You can study them since this tropical setting. And I think maybe I could stop there. So if you have any, I forgot something. I think it's, maybe I didn't show very well the geometry, and I could make much more pictures, but I didn't. And maybe it's a good way. Here's with this theorem, we can start on it again tomorrow.
Other questions, remarks, observations? Yes?
So if you start with when you look at the process of real roots, and you draw the graph of the polygon, you still have a third number of roots. Is there any symmetry that you expect on the graph?
For example, since I didn't explain it, maybe it's something important, is that the process we make respect very well the real structure. Then, if you have a real root, if you're looking at real varieties, and if you have a real polynomials, if you have a real root, maybe you cannot. Or let me think again. If you have a complex root, then you have they became in pairs. Okay. The conjugate one will be also a root. Then the multiplicity will be always even if you don't have real roots. In the other instances, you know that the multiplicity of a root is odd, you can guarantee that there's at least one real root in the classical world. Then, in fact, we work a lot of that when we use tropical geometry. For real algebraic geometry, we try to look at odd multiplicities of objects because it detects real parts of the variety. Since the complex one became always in pairs, then you can detect. And then to your question, you cannot detect. They are not both real, but you can. But it was 3. You know, there's at least one real.
Other question? Yes?
Could you repeat which is the evaluation you're considering there? You have an edge, no? You start with a...
Yeah, I make a point here will be sent to the valuation coordinate wise, or minus valuation.
given valuation, no? The drop F or the depends on the valuation.
Okay, and both the same valuation in both sides. Then you work here and evaluate, or here we'll speak only about isosceles, for example, and for each point in the variety you take the valuation coordinate wise. And the set of these points is equal to the set of points defined by the tropicalization of the polynomial. Then the idea will be in the next talks to explain how we use this tropicalization, the study of singularities, and a little bit more if we have some time.
Okay, so is there no other question? Thanks, speaker again. And we resume in